Hello my YouTube followers. In this video we're going to look at two good examples that you can we will use to find and apply mesh current method, and I hope that you enjoy the video. Thank you. Okay, so this is our example one that we look at in mesh current method. So if you remember, we have a scenario where the current source is in between two meshes. So if we take this as mesh 1, we have I1, and we take that as mesh 2, we have I2, and then we've got what we call a super mesh that is considered around this loop. So the voltage drop around this resistor 1, considering the direction of the current flow, is going to be plus minus VR1 plus minus VR2 plus minus VR3. Therefore, the equations that we make are going to be two equations. That is one equation at the super mesh, which is this super mesh, and the other equation at the current source. So when we start with the equation at the super mesh, we have the voltage sources. Vs should be equal to the voltage drops, VR1, VR2 plus VR3. And we know that the value of the voltage source is 10, and then we have 5. So this, if we rewrite it properly, we have Vs should be able to give us R1 multiplied by the current I1 plus this is R2 multiplied by the current I2 plus R3 multiplied by I2. If we replace in the values, what you notice is you have 10 should be able to give us, we've got 5 I1 plus 2 I2 plus 4 I2. Then we've got I2 and I2 which are common, and therefore the whole equation remains as 10 equal to 5 I1 plus 6 I2. That is the equation that we have at the super mesh. And then when we look at the current source, what we have is the current source going down, and then we've got I1 which is also going down, and I2. Therefore, at the current source, so this is equation 1 at super mesh, okay? And then at the current source, what we have is that our equation is minus IS, or current source, should be able to give us I2 minus I1. I2 minus I1. And if we apply the values in here, we have minus 2 should be able to give us, in this case we can consider this as minus 1 plus I2. So these are the equations that we have, two equations that we have to solve simultaneously. And if we put these two equations together, we could say we have 5 I1 plus 6 I2. This gives us 10, and then we have minus I1 plus I2. This gives us minus 2. So the simplest way we could find these two equations simultaneously is by multiplying the lower equation. You can use replacement method, you can use matrices, or you can multiply this by simply by 1, and then this is multiplied by 5, which gives you 5, 6, and 10, and here you have minus 5, plus 5, and minus 10. So the 5 and 5 will cancel out. That will be 0, which will be equal to 5 plus that will be 11i2 excuse me, that is a plus. That should be able to give you, you've got minus 10 there, and 10, when you sum them up you get 0. So in this case your I2 is simply 0 amps. And if we replace in this value in one of the equations, if we pick the current source equation, then we're able to say that if I2 is 0, if this is 0, then I1 is simply equal to 2. So from there, I1 is equal to 2 amps. And you can verify that using KVL equations. Okay, so we look at example 2 on the mesh circuits, and here we have 3 mesh circuits. So we've got mesh 1, which we label as I1, we've got mesh 2, I2, and then we've got mesh 3, that is I3. Now you bear with me here, there's an error, so that will be R4. We take that as R4. So this is R1, R2, R3, R4. And by analysis, you'll be able to tell that for mesh 1, what we have is that I1 is directly equal to the source current, which is equal to 0.5 amps. So this is sorted out because the mesh current I1 is in the same direction as the current source. Therefore, this is equal to the source current. And then we come to the equation on mesh 2. So by the direction of the current, we are going to have a voltage drop here, plus minus VR3, plus minus, sorry, so this is VR2, this is VR3. Okay, and then we apply KVL on mesh, so we consider this as mesh 2. So mesh 1 is sorted out. Mesh 2, therefore, we have the voltage source. In this case, the current leaves the negative terminal, so it's minus Vs, should be able to give us VR2 plus VR3 as the equation. Then we can expand it further by replacing, by expanding the voltage drops. So in this case, we have minus Vs should be able to give us VR2 is equal to, we have the shared currents here, so we have R2 I2 minus I1, and we know I1 is 0.5. And then when we go to VR3, so we are saying plus VR3, which in this case also has a shared current. We have got R3, we've got I2 minus I3. That forms the equation. We can expand it, so we're dealing with the same mesh 2. We can expand it and say, let's insert in the values. So we've got minus 10, should be able to give us what we have here as R2 is 8. You've got I2 minus 0.5 plus R3 is 6, I2 minus I3. So this then gives us the actual equation, which we can expand further because we've got I2 and I2, which is common, and then we've got 0.5 here. So 8 multiplied by 0.5 will give us minus 4. Minus 4, when we take it over the equal sign, it becomes a plus 4. So what we have here is minus 6, giving us 8I2. 6I2 gives us 14I2. And then we have minus 6I3. That's the equation we have for mesh 2. So for mesh 2, we've simplified the equation and we've made it in that way. For mesh 3, what we have is we have no source. So the source is 0, which is equal to, we are going to have, by the direction of the current, we have plus minus VR1 plus minus VR4 plus minus VR3. So when we add the drops, what we have is VR1 plus VR3 plus VR4 as our voltage drops. So when we expand that, so I'm going to go to a new page, but you follow the expansion. When we expand that, so mesh 3, we have 0 equal to VR, if you remember, we've got VR1 plus VR3 plus VR4. When we expand that and insert in the values, so VR1 has got shared currents, which are, if you look at this, you've got shared currents, which is I3 and I1, and we know the value of I1. Therefore, when we solve here, we've got R1, I3 minus 0.5. And then when we come to VR3, we've got the shared currents, I2 and I3. So R3, which is R3 multiplied by I3 minus I2 plus R4. If you look at R4, it has no shared current, it only has I3 going through it, multiplied by 4, or R4. So R4 multiplied by I3. And that's what we get. So when we insert in the values, we have 0 equal to R1 was 3. We've got I3 minus 0.5. And then that adds to, we've got 6 for R3, I3 minus I2, plus R4 was equal to 4 ohms, 4 multiplied by R3. And then you see that this is common. So when we multiply 3 by 0.5, we have minus 1.5, which we take over the equal sign, which is simply 1.5. This equal to, we've got R3, and R3, that is common. And then we've got a minus I2 here. So we've got 6 minus 6 I2 plus the R3, which is 6 plus 3 plus 4, which gives us 13 I3. So the two equations then that we have are the equations, the first ones that we solved, which, if you remember, we had minus 6 equal to 14I2 minus 6I3. So this is the first equation. Minus 6 should be equal to 14I2 minus 6I3. And then that was for mesh 2. And for mesh 3, we have found our equation to be 1.5 should be able to give us minus 6I2 plus 13I3. So you solve these equations simultaneously and you're able to obtain the values. I3 is going to give you minus 0.39 amps, and then you obtain our I2 to be equal to minus 0.596 amps. So you can verify this by solving simultaneously. You could multiply this. A simpler way, you could multiply this by 6 and by 14. So you could say this is by 6 and this is multiplied by 14, and then you cancel out the I2 and you find I3, which will give you 0.39, and then you replace 0.39 in one of the two equations and obtain the solution for I2. I hope that the two examples that I've shown are good enough for you to understand how we use the mesh current method and how we apply it. I surely hope that this will help. And for the next video, I'm going to look at the node voltage method. So join me and you enjoy it. Thank you and have a good day.